Welcome everybody. My name is Ullrich Pfeiffer and I'm with the University of Wuppertal in Germany. And in my keynote, I would like to present to you the work we are doing on terahertz wireless communication at my university. We are using silicon technologies for achieving real 100 gigabits per second and beyond. Now, the outline of my talk is as follows. I will first give you a motivation why we would like to use terahertz frequencies for communication in 6G. And I would present to you some of the technology options that we have available. And then from there, we are talking about some of the transceiver design challenges to implement front ends in silicon technologies. And the first example is going to be about a 240 gigahertz SiGe BiCMOS front end, which is based on an IQ direct conversion transmit and receive chipset architecture. And I will go into the details of the design, showing you some of the link impairments that we have figured out. And then in the second part of the presentation, we will look into a polarization-diversity MIMO architecture, which uses circular polarized radiation to basically increase the number of channels and the spectral efficiency to achieve a higher data throughput. And of course, that's an important part for getting towards the targeted 1 terabits per second that we are looking for in 6G. And finally, I'm going to conclude my presentation. Now, with this work, we are kind of following the pursuit to unlimited bandwidth, which seems like there is a sweet spot in the so-called terahertz range, which is the transition region between the millimeter wave and the infrared red part of the spectrum. And this sub-millimeter wave region is addressed by two communities. We have the electronics people and the terahertz photonics people. So this work here is basically purely based on electronic hardware. And I think there are a number of good process technologies available that can help us to operate our circuits in this frequency range. Now, before we go into hardware specifics, let's just recap some of the terahertz radiation fundamentals. And you know that 1 terahertz has a wavelength of only 1/3 of a millimeter. It's quite small. And also, therefore, the photon energy is only 4 millielectron volt, which is very weak. And also, if you recap what you have known from undergrad and about the black radiation spectrum, you can figure out that you can even cool down to 17 Kelvin to get the peak of the black body radiation spectrum, right centered at 1 terahertz. And you also know that, of course, when you look at the cosmic background radiation, you can create nice images. In fact, where the radiation from the black body background at 2.7 Kelvin is actually at 160 gigahertz. So that is something that is being recorded here to image the background of the universe, basically. So that is also quite high frequency if you think about it. And also what's quite interesting, you may have remembered some of the publications that we've seen in 2017 about the image of a black hole, which was in fact recorded at 240 gigahertz by the Event Horizon telescope. And here you see some of the pictures. And also, of course, if you compare the energy of the photons with that of an X-ray photon, you see that X-rays are 7 orders of magnitude higher, and therefore terahertz radiation is non-ionizing, and that is, of course, something that makes terahertz inherently safe. Of course, we have to communicate this well enough when we discuss this in terms of using it for 6G communication. And you know, all these discussions has been discussed also for lower frequencies in the past, and there, of course, one needs to look at the specific absorption rate, which is something that you need to watch out, of course. Now, let's look into electronic device technology options that we can use for these frequencies. And of course, you remember that we have very fast and well-performing device technologies available. One pronounced technology here is indium phosphide, HEMT, which have Fmax, maximum frequency of oscillation at 1.5 terahertz. And we have seen their amplifiers above 1 terahertz even showing a gain of 9 dB. Now, there are other technology options like gallium nitride available, indium phosphide, and double HBT devices with even 1.18 terahertz Fmax. Now, those technologies, of course, have not been used a lot when it comes down to high volume consumer electronic applications. Therefore, silicon technologies, of course, are one of the key players in this field, and of course you would like to implement finally stuff in the CMOS technology, in either bulk or SOI or FinFET technologies. The problem there a little bit is that the Fmax is substantially weaker. It's in the range of 300 to 350 gigahertz. And of course, there's still a much better performing technology available in silicon, which can be combined with digital CMOS technology as well, which we then call the SiGe BiCMOS technology. And here we have seen HBT transistor performances even up to 700 gigahertz. And of course, that is high enough to get into this, what people call often the sub-terahertz range. And I would like to show you some of our results using this technology here as well. The other thing is that there are other technology options available where you can combine the best out of the two top ones here. You can combine indium phosphide devices, for instance, which outperform in power, Fmax, and also noise performance, and you can combine this with the high-speed SiGe HBT transistors. Another interesting technology option that is available is to combine the best of electronics with the best of photonics. And there you have the benefit of using modulators, waveguides, and germanium photodiodes, plus you have all the silicon backend kind of available. Now we are mostly interested here in using silicon germanium HBT transistor technologies, and we can take a look at the evolution of that technology over recent years. And in this chart you see the peak cutoff frequency, Fmax, and at around 2000 we had about 200 gigahertz of max available, and that was then further pushed out with the next generation to roughly 300, and then we had 500 gigahertz of max at around 2010. And then with the recent development activities here, which were also funded by a European project called .7, we were able to achieve a cutoff frequency of even 700 gigahertz. And of course, with each of these generations, we have seen new applications kind of coming up. We had, at around 2010, 60 gigahertz circuits, 700 gigahertz radar applications. And now with these faster devices, we are moving really up into this terahertz domain, where we have seen a lot of imaging applications as well as communication circuitries. And of course, there's not an end in sight. So it is expected that this can be further improved. There are some device modeling and device performance simulations that have shown that you could even go up to a cutoff frequency beyond 1 terahertz with these devices. So there's a lot of room for improvements, and of course, therefore, we are quite excited about that technology option. So how do faster devices help us for 6G? You can first take a look at fundamentally operated circuits, where you can actually move to higher carrier frequencies if you have a faster underlying transistor technology available. You can also have more gain per stage, which means you can get away with fewer gain stages in amplifier design. You can also trade performance for larger bandwidth, which helps you, of course, for high data rate throughput. You can also use the faster devices to bias them at a quite lower current density, and therefore you can improve power consumption, which in turn then also improve the efficiency. So you can get to higher power efficiency of your amplifier and your overall circuitry. You can also kind of combine amplifiers more easily because you can kind of trade the parasitic effects for better power combining techniques. You can also lower the noise figure because you have more gain in the first stage, and therefore the overall noise figure of your receiver is optimized. And finally, in subharmonically operated circuits, you can basically jump on to a lower harmonic number, which improves conversion efficiencies. And that also in turn gives you higher output power and lower noise figure of your circuitry. At millimeter wave and terahertz frequencies, we have of course seen also many other applications. We have seen many that are related to imaging and sensing, for non-destructive testing, for security, for biomedical applications. Space is something that we've discussed before. Material characterization, spectroscopy, and super resolution imaging are hot topics that are a major player here in this frequency range. There are also more industrially relevant kind of applications that are related to radar. At 77 gigahertz automotive applications we've seen at 120 gigahertz, 240 gigahertz is something that gives us better resolution, for instance. Spatial and range resolution is important here. But also in consumer electronic applications, we have seen from the Google Pixel phone, for instance, that there is gesture recognition that was introduced at some point. There's also 3D imaging possible with radar applications where you get depth information about objects. Patient monitoring is an interesting application that is available at these frequencies. But of course, we are talking mostly here about high-speed communication, and you have seen that there are other bands, of course, over the past that has been addressed. But really, there's this new IEEE 802.15.3D working group that was defining in 2017 the frequency band of 252 to 322 gigahertz for terahertz communication, and that can of course be an interesting band for 6G, where you will see that are data rates of 100 gigabits per second possible. That can be used for various kind of applications like high-speed interconnects or the connection between data servers, for instance, but also for longer range communication, as we will address in a second. Now, before we go into communication, I would just like to show you a few hardware implementations that are related to terahertz imaging. And here, for example, we see some work about a terahertz generator, let's say. It's not really a transmitter where you can run data through it, but it's kind of a source that is made out of 8x8 elements. And of course, that is an important question that also comes up later when we talk about MIMO. You know, how many elements could we then possibly integrate on a single chip? And here we were able to create at 420 gigahertz a radiated output power of about 10 dBm in total. So that combines all the power that is emitted from all these antenna-coupled oscillators in this sense. Of course, this creates a bit of a power and heat dissipation problem because the efficiency of those sources are not particularly high. But that is something, of course, that is related to the source, and we can do, of course, similar kind of things at the receiver side. And this is another example here where we have actually implemented cameras that are made out of 32 by 32 pixels. So this is a kilopixel kind of camera array. So here we have 1024 antennas that are coupled to a detector. That all fits onto a silicon die that only has a dimension of 3 by 2.7 millimeters. This also includes all the readout electronics, ADCs, and all the stuff that we need later on also for communication. This whole thing is quite compact and it's attached to a silicon lens. We will discuss silicon lenses in a second. Now, of course, you can scale this even higher. You know, if you want to think about massive MIMO implementations, for instance, here you see an example of a 3 by 3 camera array. So here you have just 9 times as many pixels available, and that means you have 9,216 receiver channels available. Of course, again, this is not for communication, it's for imaging, and here you see some of the data set that is being provided here in this figure. Now you can imagine that, of course, it would be nice to have here, 9,000 independent communication links available. You could, of course, scale your data rate accordingly. And all the network people would probably be quite happy if that would be available with a data rate of about 100 gigabits per second in each of these channels. Unfortunately, yet this is not possible because the amount of hardware that's required to implement a full communication transceiver is much larger than just an antenna and a detector, and therefore we need a lot more area right now to implement hardware to reach about 100 gigabits per second. And this is what we will discuss now. So when we first looked into communication, we were thinking about implementing something very generic, some kind of generic IQ transceiver that uses some moderate spectral efficiency between 2 to 3 bits per hertz at 240 gigahertz center frequency. So we were thinking of implementing a rather broadband RF band here that we mix down then to 25 gigahertz IF. Which would give us something like 50 gigabits per second in I and Q respectively, and that should be something that we can use for 100 gigabits per second. Important though is to remember that it is quite challenging to provide the carrier frequency and the local oscillator signals. So in this case here we had to look into how we generate the LO by using a multiplier chain with respective multiplication and amplification stages. And then also we had to implement, the quadrature signal generation, which is then also quite wideband to also provide channel selection features and so on. So that was kind of our idea. Now, the question though is that anywhere practical? And for this, you have to look into the link budget estimation, which is shown here for a QPSK, moderate spectral efficiency. And you can look into various kind of transmit powers and noise figures for different kind of RF bandwidth. And of course, if you increase the bandwidth, the total noise integrated over this bandwidth increases. And when you really do the math here, you see that for anything that seems practical at the moment, you can only get to very short ranges. And the only way really is to include high directivity transmit and receive antennas. So it is not expected that the hardware will be making much improvement on transmit power or noise figure that is orders of magnitudes better than what you can have today. So you really have to include antenna design and packaging aspects to really reach ranges in the area of about 8 or beyond 10 meters. So to achieve this, really, of course, we have to look into the circuit trade-offs on noise figure, bandwidth, range, antenna gain, and packaging. So it needs to be an all-inclusive design approach that takes all these parameters into account. And this is what we have finally done. So we started out in 2015 developing such a transmitter. Also, we looked into different kind of receiver implementations. Some of them had amplifiers included as a low noise amplifier, which we call an amplifier first implementation. And we also had kind of various variants of that circuit without amplifiers, which we call mixer first hardware implementation. Now they all kind of differ in their noise figures and bandwidth, and we were really wondering what kind of implementations, what kind of impact has that on the overall system performance. Now here you see the chip micrographs and the packaging of the related hardware. On top you have the transmitter. You see on the left side the amplifier first receiver and the mixer first receiver on the right side. And you see that the hardware modules kind of all look the same. We use a chip that's directly attached to a silicon hyperhemispherical lens. And then we use regular wire bonding and attach it to an FR4 printed circuit board. So the board technology is not particularly expensive. And all the RF capabilities and circuits are within the chip, so we don't really have to feed high frequency signals onto the printed circuit board. Now here you see one of our first live demos that we were operating in 2016. It is a really simple demonstration of wireless communication where we are just using the very broadband IF signal to directly interface to an HDMI DVB-T signal from an antenna that is well within the bandwidth of this hardware, so you can directly transmit the antenna signal and of course all the channels that are part of it. Now that one can actually go through cardboard, of course, because that's one of the nice benefits of terahertz, that it can penetrate dry materials, and of course you can block it with your hand. Now, the question though is how much data rate can you actually put through this channel? Because that is mostly just a very simple link demo, but it does not show you the full capabilities and not the impairments that are related to this hardware. So that was our next question. How can we actually characterize the full performance and understand the link impairments in these transceiver circuits? Now, this is something that we have tried to address here in a number of data rate measurements. We started out evaluating different kind of modulation or cancellation orders like PPSK, QPSK, and then went up to even 64 QAM. And we were looking into the achievable ranges here. Now, you can, of course, obviously observe that there is a difference in the data rates that are feasible. And if you compare the different hardware, and you see here on the left side the amplifier first, and on the right side the mixer first kind of results, you see that the best results, in fact, we were able to get with the mixer first implementation. And the reason is not that this mixer first has better noise figure, or SNR, it is really because there is a more flat bandwidth. And why that has better performance is something that we addressed very precisely. And this is part of the RF link impairments, of course, that you kind of have to deal with in these implementations. Some of them are kind of obvious that are related to the spectral purity of the local oscillator. There's also, of course, because of that, kind of a lot of signal to interference that is being created at the receiver side. Also, you have LO feed-through on the receiver that kind of limits also the IF bandwidth, how high you can go. But of course, there's also something that's called IQ crosstalk, and this is just something I would like to illustrate here in this chart. You have on the left side the in-phase signal of the baseband, and on the right side the quadrature signal. And when you start mixing this with the sine and cosine signal, and you add it later on, you create a complex spectrum that is indicated here. And when you later kind of demodulate it with a cosine on the left and with a sine on the right side, you see that ideally you cancel the respective I signal in the Q channel and the respective Q signal in the I channel. So ideally you should only get a clean output without any crosstalk. However, that's not the case. And you see this if you assume that there's some asymmetry in the channel. And if that is the case, then you see that your signals will be slightly distorted across the bandwidth. And then when you do the demodulation of the I signal with the cosine again, you will see that you are ending up with some remaining crosstalk from the Q channel in it, as well as on the other side. If you demodulate the Q channel, you will end up with some crosstalk from the respected other side, and that kind of creates some kind of interference that's quite large. And that was some of the limitations that we were facing when we were moving to these very broadband signals and systems where the RF bandwidth kind of is limiting. Now, nevertheless, the signal carrier was high enough so that we were able already to address a number of channels within this new standard. You see this here, we can cover 4 channels of 2.16 gigahertz or 1 channel with 8.64 gigahertz. And of course, we can also go larger distance in case you would like to increase the directivity of the transmit and receive antenna with some external antenna gain. This is something we can discuss later a little bit more. So how about larger data rates? 100 gigabits per second in principle are already quite nice, but we would like to increase that by combining multiple channels together. And one way of doing this would be to use a polarization diversity. That can be cross-polarized, or in this case we are using circular polarized radiation. So we have to have an on-chip antenna that creates left-hand circular and right-hand circular polarized radiation at the same time. And then on the receiver side, we need to come up with a hardware implementation where we can separate these two polarizations. Now, of course, you can see that the hardware in these block diagrams are kind of extensive because you have to double all the transmitter circuitry as well as the receiver circuitry. And on top of that, you need to consider the 90-degree hybrid implementation that gives us the 90-degree phase shift that is required for circular polarization. So all that, of course, needs to be implemented, and all of these IOs, of course, need to be considered over a very large bandwidth. So you know that for the 100 gigabits per second, we need a very high-speed IF interface down to the printed circuit board. And this is, of course, something that we were routing differentially in the previous hardware. In this hardware, though, because of the excessive wiring that's required, we went single-ended. And that, of course, has an implication later on, as you will see, on the achievable data rate. But nevertheless, the proof that we wanted to make here is, can we double the data rate by doubling basically the hardware and using a circular polarization diversity MIMO? And that I would like to show you now in the following slides. And here you see the chip micrograph implementations of this. On the top here, you see the receiver design, and the lower part you see the transmitter designs with the respected IQ portions of each of the channels that are then hooked up to a dual polarized antenna through a 90-degree hybrid, which is required, of course, for the circular polarization. And now the question is, how much crosstalk kind of is related to this implementation. And there can be crosstalk, of course, directly on the chip, but also through these hybrids. There can be some signals of this red transmitter can actually make it over to the green receiver on the other side if there is, for instance, some imperfection. First, we are going to take a look at the upconversion mixer circuitry that we are using in the MIMO system. I don't really want to go too much into circuits here at this point, but just to show you again, the basic hardware that we're using is a pretty standard kind of Gilbert cell upconversion mixer. But as I said to you before, we are using here basically a single-ended drive at the input, and the other side is kind of terminating to 50 ohm. That's not an ideal situation, so it's still a double balanced Gilbert cell, but just using a single output. And that, of course, is not ideal in terms of EVM and also in terms of output power. So a differential drive, of course, would have been something that we would like to implement, but really it is I/O limited. Now the down conversion mixer MIMO circuitry is shown here in this figure. So here again, we're using a switching quad down conversion mixer, and it's again a double balanced Gilbert cell, but here we are also using just one single-ended output. Now that of course also increased the EVM and lowered the conversion gain, and also has an impact on the noise figure. Now that of course is something that we had to do because of the limited I/O. It's kind of a pad limited design in this sense if you want to design that all over a very large bandwidth. Now in this slide you see some of our MIMO antenna simulation setups. We're using HFSS to do a full wave simulation of the antenna structure, including the feeding hybrids. And the layout, of course, needs to be compensated to keep the phase constant over all radiators. And that kind of is a co-design of the coupling structures as well as the antenna feeds. You can also observe the field rotation, which generates the circular polarization radiation. Antenna implementation. Now, this is something that we have investigated here. This actual ratio, for instance, is some of the important parameters here that were measured. So that is very close to 1, in fact. And on the directivity side, you also see that the directivity is about 25 dBi, as much as we have discussed in the link budget, for instance. So we have that directivity, of course, on both sides. Now, in this chart, you see some of our antenna measurements. Here we measured the antenna pattern as a 2D contour plot for the right-hand circular polarized radiation at a 240 GHz carrier for the transmitter. And in this chart you see that we have a pretty rotationally symmetric beam with 24 dBi at the center, and we have a pretty high side lobe suppression. And it really is important here to have a very nice clean beam, which is of course a benefit that comes from the hyperhemispherical silicon lens that we are using as a secondary radiator to our on-chip antenna that is integrated together with the circuit. Now the question is, how well are the different polarization isolated from each other? That is of course an important parameter that is measured here, and you see that we are always better than minus 17 dB and sometimes even down to minus 30 dB. And this is all independent of the relative orientation of the transmitter with respect to the receiver. So that really solves one of the big issues of alignment, because before in these linearly polarized links, you always have to make sure that you are not only facing the transmitter receiver line of sight, you also have to make sure that they are of the same orientation. And this is of course a big advantage that comes on top of the additional higher spectral efficiency that you have here, that you don't really have to worry about isolation with respect to the relative alignment of your transmitter and receiver. So let's look at the performance of each of these channels. First, we were looking here into a single channel, and we were operating it at QPSK and tried to increase the symbol rate basically here. So you see in the chart here, we started out at 20 gigabits per second, and then we increased the symbol rate to reach up to 55 gigabits per second. This was the highest data rate that we were able to get. And you see that the EVM, of course, at that data rate was also pretty high at 30%, but still we were able to operate this link. And next, we were combining two channels at the same time, and we were almost getting the same kind of performance. So we reached again 55 gigabits per second in each of these channels, which then added up to 110 gigabits per second over 1 meter. If you operated at 40 gigabits per second, then you could even go up to 80 gigabits per second in both of these channels over a range of 2 meters. No? So we kind of get the same performance that we got on every single channel just twice. And that, of course, indicates that this kind of concept of increasing the data rate through two orthogonal orientations, circular and left and right polarization, kind of works. Now, when you look at the RF performance, you see that we got an output power here of 7 dBm. And also you see the measured conversion gain here that we got, that was above 15 dB. Noise figure was better than 18 dB. Also, although noise figure does not seem to be one of the critical parameters here in the sense when you compare it to all the other impairments that this hardware kind of were facing. And this refers back to the earlier discussion that we had. Now, the leakage is something that I mentioned before on the antenna. That can also be through the chip, and this is something that we have measured here. So we try to kind of convert down the signal that one channel kind of passes through the 90-degree hybrid here to the other side. And you see here, that's another source of error, that this isolation kind of was on the level better than minus 20 dB. And that is something, of course, that also needs to be considered. Now here you see the packaged chips and the PCB design, very similar to the previous hardware that you have seen. Now we have just recently extended our measurement capabilities in my lab. So we are setting up right now a 6G communication testbed where you have 6 real-time oscilloscopes from Tektronix available and also 6 AWGs, which you can actually combine in different ways to characterize terahertz MIMO systems. So not just only 2 polarization as I've presented you in this workshop presentation, but you can increase the number of channels here up to 3 full IQ differential transmit and receive chipsets. So if you're interested, please drop me a mail or go to the link that is provided here on the slides to get some further information. Now finally, just some constellation diagrams for different kind of ranges. Here on top you see the QPSK constellations over 1 meter, and you see this for the left and right hand channels, and as well over 2 meters on the lower part of the graph. And you see as well here, of course, that we are kind of running into the LO feed through here on the IF, and you see the carrier also being transmitted through. Now, when we come back to our initial link budget estimation that I presented to you, we have seen that we can, of course, reach data rates of 100 gigabits per second and beyond, 110 gigahertz in a dual polarized MIMO system. But nevertheless, if you really want to increase the range of your links, you would really have to increase the antenna gain. This is basically the only way at the moment that I think is possible to reach up to ranges of about 100 meters. No? But of course, if you do that, that can be done with a lens of a diameter of 6.5 centimeter, for instance, or a mirror. There should be no reason why this hardware should not be able to operate over larger ranges. Overall, if you compare our results here, one can conclude that this hardware that was published in the transaction of MTT in 2020, last year, that with this data rate kind of we are well above the 100 gigabits per second, and this hardware compares very well with recent publications. Now, for reference, of course, I also included here the relevant literature. Now, this brings me to the conclusion of my talk. We have seen that 110 gigabits per second is possible in a wireless communication in a silicon germanium technology. We can implement 240 gigahertz chipsets with rather inexpensive chip-on-board technology, including a secondary silicon lens antenna, which gives us already quite some reasonable antenna gain. Combining this, of course, later with a mirror or lens could help us to even go to 50 dB antenna gain that is required kind of to reach up to 100 meter. There is the other part of the presentation that kind of has shown us that we can extend the spectral efficiency with polarization-diversity MIMO system architectures using circular left-hand and right-hand polarization radiation. And here we have seen that we can actually increase the data rates by a factor of 2. The other important benefit that this has, that we are getting rid of this alignment problem that we had to have well-aligned linear polarized links, and here in a circular polarized radiation scenario, of course, we can rotate the transmitter with respect to the receiver without losing any data. And finally, of course, we have discussed the RF link impairments that need to be solved. And of course, later on, you need, of course, to think about the whole RF front end being connected to the baseband. And there, of course, is still a big question how you can actually implement a digital baseband and what kind of ADC, what kind of digital baseband architecture is being interfaced to these RF front end modules. That's still an unknown problem. And you know that the hardware that is required on the digital side is also kind of power consuming and therefore can also be a limiting factor. Now this brings me finally to the end of my talk. I just would like to thank my students and my research staff at the ISSCC, who of course have contributed to all the work that was presented. And I also would like to acknowledge the funding agencies and also our collaborators. So finally, I'm happy to take any questions you might have. Thank you.